Okay, so it's 7 o'clock and we'll get started. If you tried to turn up last week and you got our message that we had to postpone, I'll just say quickly that we have no idea why, but it seemed to be something to do with the quality of the internet service from the States and maybe something to do with the fact there was an election going on at the same moment, but we seem to be okay now. If you do have any technical questions, then put something in the chat and we'll see if we can help you. So I'm Tony, and as you probably know, we've been working on a mastery curriculum for 4 or 5 years now, and it's taken the shape of a framework for 5 years, a course, books, and as you'll see in this webinar, we're doing some more things to try to really cover all the bases that you might need if you're putting mastery into practice. That's our vision anyway. Welcome to Gemma, my colleague. Would you like to introduce yourself?
Yep. Hi, everyone. Yes, I've been working with Tony in Mastery Science now for a few years. And before that, I worked with him on lots of different curriculum projects. And before that, I was a science teacher. And my main role in Mastery Science at the moment is to write the resources.
Thanks. So, okay, so some of you have done this starter activity, and the results show fairly clearly that most of you can do 1 and 2, but that 3 and 4 are harder. That's exactly what we expect. The question is, why is there some kind of limit on the number of digits you can multiply together in your head? So Maria suggests that it's to do with, we have lots of sound problems here. I'll pause for a minute. Some of you can't have sound, but I think you can hear me when it's working with you. Gemma's saying reload the page if you have issues. So Maria hinted at the answer here. This is to do with working memory. We're going to have a little tour into working memory because it helps us to understand why these principles of Rosenshine actually are necessary. So we're going to be looking at 2 of these principles to do with modeling, explaining, and making things simpler. And as a quick review, remember last week's webinar was all about reviewing what people already know. So if you weren't there, what we were trying to look at was how to make sure that students are actually kind of getting the knowledge that they need in their heads. And that's going to be even more critical when you see why working memory makes that necessary. So we're aiming for more than the picture on the left, right? It's not enough just to have some kind of basic memory of the facts. We want that memory to be, if you like, a schema, an integrated bit of knowledge that links up with things that connect to it, which means you can access it, which means you can do meaningful things and apply it, which is all about understanding. So that is the goal of all, I hope, of our teaching and learning and what cognitive psychology would recommend. It's really important to have that goal, because if you didn't really care about understanding and you thought it was enough to have some factual knowledge, you wouldn't bother with these principles. Now, what that experiment is going to show us is that we have a bottleneck, right? You can't process everything. In fact, only a tiny amount of what information you take in. So let's go back to that example and see why you couldn't do, let's say, sum 3 and 4. And it comes down to the fact that when you do this in your head, you have to store intermediate results. You would write them down on paper if you're doing the column multiplication method, but if you have to put them in your head, then I think number 3 involves storing 4 intermediate results as well as manipulating the numbers in your mind. So that's actually 5 things you've got to remember and process all at the same time and keep them going. And then when you get to number 4, there's 5 intermediate results. So that's altogether at least 6 things that you're doing at the same time. And the research suggests that we are basically limited in our mental capacity to 4 or 5 new things or things that we're trying to process at once. And that is it. And if you go higher than that, your working memory fails and you can't get the answer. But more importantly, you're not actually going to transfer anything meaningful to long-term memory in that case. So you don't really learn anything. You might even get the right answer, but you're unlikely to have learned anything about the process that would help you the next time. Now, this is really important, but if you believe Dylan William, who courses assessment for learning in person, he would say this is the most important thing that teachers ought to know. It's actually become quite popular in recent years, cognitive load theory, which is, if you like, a kind of instructional version of working memory. It's saying, because of the working memory limitation, this is how you need to teach. Is it the most important thing? Well, I'll let you decide that in a moment. What does it actually involve? Does anybody know? You've probably heard the term, but what does it mean? Well, I can see we have some sound problems here. I don't know why that is. If that's the case, don't panic, because we will put this online. Anybody know what is going on with cognitive load theory? I'm pausing here for some chat answers. Okay, well, that's fine. We didn't know that one because actually it is a bit complicated. Get ready for this. The theory says that there are 3 parts. Oh, Darren's figured it out. There are 3 parts to the load that any new information puts on your memory, right? This is a theory, okay? The first part, called intrinsic load, is to do with the complexity of the actual idea that you're presenting. So if you're presenting, you know, something simple like 3 kinds of rocks, there's a low load probably, whereas you're presenting relativity, the load is extremely high. And there's not much you can do about that except to put it into smaller chunks. So that's one lever that you can pull as a teacher or a designer. You can say, well, that's a bit too difficult. I need to split that up. The other levers you can pull, first of all, are this one called germane cognitive load. What that means is, how much actual processing do you want them to do, right? You actually want people to do mental arithmetic, don't you? Because you want them to be able to get through that part of the problem very easily and concentrate on the higher level things. And so we want kids to be able to do that. We want kids to be able to, let's say, use scientific thinking skills. We want them to figure out, you know, how a scientific model works. There's a lot of processing going on there. That's germane, that's relevant, appropriate, what you want them to be using their working memory for. And on the other flip side is extraneous load, which is, if you like, the bad side. It's everything that distracts them from the processing you want them to be doing. So that's like bad textbook design, when you have these fabulous facts that distract students from the main idea, or whatever else it is that's unnecessary and adds too much load and stops them, you know, concentrating on the main point. So I hope that's actually quite helpful. That's what cognitive load theory is. But as you can see, while it's a set of levers that you can pull, it doesn't really tell you how. It doesn't tell you whether a particular, you know, page in a book or worksheet is going to be too overloading or not, right? You won't know that. So what I think is helpful is to know that working memory is, if you like, it's a set of things going on inside your memory system, and much of the time it works fine, but there are certain things that will put it into overload, and when that happens, no learning takes place. It helps me to think about what's going on in my brain. And recently, in fact last year, scientists have come up with a kind of metaphor for this, which maybe will help you remember why it's really important, which is that there's three parts of your brain that are kind of juggling the information between them. It's like a game of catch. So the prefrontal cortex is the one that's modeling the world, right? You are generating all the time models, predicting what's going to happen, which drives your behavior and kind of working out what happened before. So you're doing this huge amount of processing that's going on. And to guide that, you're taking in sensory information from your eye or other senses. And you've got these three parts that are kind of working together to go, this is what I thought was going to happen. This is the new information. Yes, that's what I thought. I'll carry on doing this. Or hold on a minute, that's not working. I better update that model. That's what your brain's doing all the time with the new information. And while there's only a certain amount of information that you're paying attention to, you can cope. But once it gets beyond 4 or 5 bits of information, it turns out that your modeling system, the one on the left, the prefrontal cortex, cannot cope with that new data, right? It's just too much. And so the signals between those three go out of sync, like dropping the balls that you're juggling. And that's when you feel that sense of overload and you just can't keep the information in your head. So that's really what we're trying to avoid. But at the same time, remember, we have to make sure that they're learning in a meaningful way, that they are actually processing things and integrating it with existing knowledge. So that's a challenge. There is no easy answer to that challenge. You want it to be difficult enough to get the meaningful learning, but not so difficult that it causes overload. I will briefly pause in case I've given overload. What do you think? Did that challenge kind of reinforce what you already know? Is that surprising on you? Is that what you're trying to do all the time? Comments? Brief pause. Yes, from Darren. That made sense. Okay. Because I think that's the backdrop to looking at the Rosenshine principles that will help us address this challenge. Pitching things at the right level. Yes, that's what we're doing. But I hope this perspective makes it a little bit more precise how we do that. Okay, moving on. So the two principles that we're focusing on here are to think aloud, to model what we're doing and thinking, because that makes it easy for someone else to kind of observe and not have to do it themselves. So that's reducing the load, and breaking things down into small steps, explaining them, and using ways to reduce the actual novel amount of information. And this is the agenda. We're going to focus on 2 specific strategies that exemplify those principles. One to do with ideas, which will be analogies, and the other one to do with thinking skills. Actually, I'll show myself here. I'd forgotten that. So just to know that this is really me in person here. We're going to do those 2 bits. I'm going to give you the kind of principle of each one, and then Gemma will give you an example of how that works in practice. So we'll start with analogies and ideas. First, analogies. Now, how many of you use analogies in your teaching currently? You can just say, yes, I do, or something like that, or no, I don't, if you'd like to chat that. Do you use them at the moment? Consciously? Yes, 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 most of the time. Yes, 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 good, good. Or you possibly even do it all the time. Right. Okay, great. So why do you do it? Oh, great. Lots and lots of yeses and mostly. Good, good, good. Well, we hope that we're going to add something to your repertoire here, not just tell you what you already know. Why is it a good thing? Well, here are 4 of the usual reasons that the research supports. When you've got an idea that you can't visualize, you really need to engage that part of your brain in doing the thinking. So you're providing a kind of support for that visualizing function. And so you're trying to find something that they're already familiar with, that they can visualize, which is similar to the thing that they can't. But in terms of the working memory, you're reducing the amount of novel information, because now you're saying it isn't new at all, right? It's very much like something you're already familiar with, and I'm going to show you how it's like that. Essentially, that's saying, okay, let's take what you know about this thing, and then all we have to do is think about the relationships between what's old and what's new, which really does reduce the load on working memory. And then there's actually more subtlety to it, which is if you work with the new idea and the familiar analogy together and you look at the connections, that teaches you quite a lot about the underlying idea. So if you kind of go, well, how is, the flow like current? And you look for the similarities and the differences, you can see you're getting a kind of more nuanced idea of what current actually means. By the way, I'm not endorsing the water analogy because there's lots wrong with it. I just thought this was a popular one for the example. And research also supports the idea that when you have a good working analogy in your mind, it becomes easier to apply the idea because clearly you understand it in some way. You can use that in a new situation rather than you kind of learned some explanation you don't really get. On the flip side, and let's be careful here, these are disadvantages, but they're not showstoppers. The first one is that the analogy, in fact, is too complicated and students don't get what you're talking about, right? So in this case here, if you do water pipes in your house, you have the danger that they may not know, familiarity with that, and they can't kind of work out what the pressure means. So it just doesn't work. On the other hand, it can also be an inaccurate analogy, so much so that it leads them towards wrong ideas. So we have to be careful. And as always, if I'm kind of trying to adopt a new strategy, I'd rather try it myself and examine my thinking as I do it to know, okay, that makes sense, or I can't really get my head around that. And I thought I'd do the same with you. If you're not in the habit of analogical thinking, it's quite useful to put yourself as a kind of subject through one of the classic tests of why analogies help. And you'll learn quite a lot, I hope, from thinking about your thinking while you're doing this. So read this problem. It's called the tumor problem, and see if you can come up with the answer without an analogy. If anyone can figure it out, do put it in the chat. Most people, by the way, don't. Okay. So this one isn't as new as I thought. So I hope you realize that this is a problem, right, that is not obvious. And so you're kind of putting yourself in the same position as students who have a problem that they can't figure out what's the right equation or concept to use to solve. And so what do? Right? Well, if you don't know the answer, one way to solve it, of course, is to try and change the problem into something that's more familiar. And so that's what the experimenters did. They presented a more concrete, familiar example, the analogy. So have a read of this. Okay, if you've read that, the answer then to the analogous problem is right. And we have some people who've already jumped to the answer for the tumour problem. So you've got this idea of splitting things up, and then you go back to the tumour problem, and it's pretty obvious what the solution is. And when they did this, of course, they didn't give all the sort of help that I've just talked through here. It was very much a read and do thing. So it was actually quite a bit harder. And they found that students who actually got 2 analogies made a big improvement after seeing the analogy on the problem. But if they'd only got 1, they often didn't see the relevance. So that tells you that there's something about the process of making the connections between 2 similar examples that's fundamental to building this idea or schema. You actually need very often more than 1 example to compare. So we have to do that with the students to make sure they do see the connections. And in fact, if they weren't told that this was an analogy they were supposed to use, very often they didn't. So you have to be really explicit and helpful. There's no sort of like magic here, but it does help. And so we can kind of extract some general principles of how to teach well with analogies. They do work. If you choose good ones, you have some explicit way of talking about what the thinking they're going to be doing is and helping with that, that you follow a number of steps that make sure that you do these connections properly. And as you'll see, deal with the issues about analogies. And sometimes you find that 1 is never enough and you need to use several to give a proper picture of the idea. So that's the kind of principle. Now let's see, what does that look like in an actual unit? And I'll let Gemma tell you about one.
Hi. Yeah, so I'm going to show you an idea that you can use analogy when teaching about cells. And the analogy is called the cell factory. And some of you might have come across this before, you might already use it. Let's have a look at it. So the problem that you might face when teaching about cells to students is that they usually just view cells like this diagram here in a book. So like a flat 2D diagram with different parts in it. And they might know the names of the parts and they might know their functions, but actually thinking about a cell as this dynamic living thing where all the parts are playing a role and they're working together to do all these different jobs, it's really difficult to visualize from a diagram like this. So this is where you can use a model to help students with that complex idea. So Tony introduced it here then that there are certain steps that you should take in order to use an analogy effectively in the classroom. So what I'm going to do is to go through each of these steps using this cell factory analogy as an example. This is taken from the textbook chapter that we're currently writing. So all the examples I'm going to show you are from that book. So the first step you need to do is to introduce a target and the source. So you'll be teaching about cells. The cell is a target concept. So students should be familiar with a cell, all the different bits and what they do. Now you're going to state the analog and describe its main features. So we chose to use a factory because it really connects very well with a cell. So the parts of a factory, it's easy to map that onto the parts of a cell. Now there are some disadvantages to using a factory in this example. Some students might not be familiar with what happens inside a factory. They might not know what we mean by an assembly line. So that could stop students from fully engaging with this analogy. So it might be that you want to show your students some video clips of what happens inside factories, some assembly lines, just to get them familiar with the model before you move on. Then what you do is you show the target, so in this case what happens inside a cell, and identify the relevant features of both. And you can see how we've designed this. If we go back to the factory, you can see we've laid it out in a certain order and we've got arrows connecting each of the parts to sort of guide you through what's happening. And we've done the cell in a very similar way. So we've got the diagrams in the same place, and we've got the descriptions using very similar language, just to really reinforce the similarities between them. So then the next thing, as a teacher, you would go through and connect some of the similar features just to really point out how the analog is similar to the target. So in this case here, I'm looking at the nucleus and the ribosomes of the cell. So the manager in the factory is like the nucleus in the cell. The manager gives instructions to the assembly lines on how to make the gadget. Then the assembly lines take the bits, put them together to make the gadgets. So if we look at the cell, the nucleus contains instructions to build a protein, and those instructions are the DNA. And then the ribosomes then use the instructions to make the proteins. So you can see the connection there. Now the next stage is that you get your students to make other connections independently. So you've given them a worked example. Now can they make the same kinds of connections with the other parts of the cell? And in the textbook, we have these speech bubbles which come on the side of the diagrams as they read through to get them sort of thinking and processing what's going on as they go through. And then we have questions at the end to check their understanding of using that model. Point out. And then it's important that students get more practice at using the analogy to form, so they can use that model of the factory to answer lots of different questions about processes in the cell. So as I said, we put this in our textbook, and that textbook did go out to quite a few teachers and they used it in their classrooms, and so we got some really good feedback on the model. So here's just a couple of the things that teachers said. So they thought it worked well with the lower ability group that sometimes have those difficulties making those connections, and they were able to use it later on in other concepts, which is great. They're actually using that model further on. And it is a unique feature in a textbook. I don't think you very often see using modelling in textbooks. Okay.
Thanks, Gemma. I know there's a few sound problems. I hope you've been able to reconnect if that's happened. So that's the section on teaching ideas with analogies. I hope that helps. We'll now move on to what can we do about thinking skills, inquiry skills. And we'll show you a technique that we use to model our thinking and simplify and reduce cognitive load. First of all, I'd like to justify why we're going to spend a lot of time developing something for inquiry skills. Because actually they appear a lot more than we think. So try this exercise, play spot the skill. What skill do you think each of these two questions is testing? Put something in the chat if you know. Yes, good. We've got the first one, interpreting data, analyzing data, right? Graph interpretation, yes. Lots of different names, but we know what we mean. Looking for relationships and patterns in graphs. But the second one, what does that tell us? The second skill is slightly different. Reading very small print. Yes, I like that. The second question is, give one reason why the student could make this conclusion. That's a much more kind of vague skill. So we have explaining concepts. There are lots of ways you could describe that skill. Reasoning, absolutely. Looking for evidence, yes. We've given that skill a name, essentially what you've said, which is to support a claim with evidence. A claim being any kind of statement of something that you think is true, and the evidence being why you think that. But the evidence obviously has to be scientific evidence. That's what it's testing. Now, what about this one? I'll give you a clue. It's related to supporting claims with evidence. Anyone be prepared to have a punt and say what you think this skill is, or skills? Yeah, we've got lots of things to do, evaluation, interpreting data, absolutely, yeah. One of the skills that is definitely there, which is sort of hidden a bit more, is, as one or two of you have said, is actually looking for multiple pieces of evidence, right? Because you're trying to justify a conclusion. And in fact, there's a lot of different evidence, a lot of different data in there from which you can pull evidence about. So you're looking for, to find each bit of evidence and to decide whether it supports the conclusion or not. And you've got to find evidence, and you've got to have reasons for each piece of evidence. So there's quite a lot to do there. And I hope you can see that's a kind of more advanced version of the previous skill, where you had one piece of evidence for a claim, and here you've got lots of pieces of evidence, and you've got to do more work to support your conclusion with a proper justification. So it turns out that kind of supporting claims with evidence and reasoning, if that's what we can call it, is everywhere, because that is a fundamental practice of doing science, whether it's processing results and data from an experiment, or whether it's actually determining, you know, what's the correct value on an oscilloscope, or which point on a motion graph is the one with the maximum acceleration, or a social scientific issue. It pops up everywhere. So we think this is one of the most important parts of inquiry or thinking scientifically skill. And so we're going to teach it explicitly. In fact, although we're focusing on this one, there are actually 24 skills that you can pick out of GCSE questions, and we really should do them justice by teaching them. Because if we don't teach them, right, we're expecting students to pick them up just by practice. And I hope that our earlier section on working memory tells you that it's unlikely that all the students will do that. Yeah, because some students don't actually have as much working memory as we'd like, which actually means that they're probably spending all of it doing the question and not very much of it thinking, I think I'm learning the skill of support evidence with reasoning. Yes, I must do that next time, because that requires them to kind of be able to think about their thinking while they're doing it, which is quite hard. So basically the solution to the fact that lots of students never learn these thinking skills is you have to make them explicit. You have to teach them. And once you've taught them in year 7 and 8, we think, and practiced it in year 9 and 11, hopefully then it's in long-term memory. And once it's there, it doesn't actually take up space in your working memory, and therefore you've got some left over to actually solve the problem. So this approach is based on the limitations of working memory too, but it isn't the technique we're going to show you. The technique is how can we teach this in such a way that it isn't overloading? And there's probably lots of acronyms. We happen to choose this one, which came from the Scouts originally, which is a nice 4-step way of breaking down skill acquisition. 4 steps being explain why you need it, where it fits, then demonstrate, show exactly what to do, then guide, give the students a chance to use it, but with your help, and then let them do it independently. You'll probably recognize this as a kind of gradual release responsibility, as well as being edge. So this is Gemma's role, isn't it, Gemma? Am I taking your bits here?
It's okay, you can do it, Tony, if you want.
Sorry about that, Gemma.
It's fine.
I just carried on. So you take over.
Okay. All right. So what I'm going to do again is I'm going to show you how you might go about doing this in the classroom using some of our materials to demonstrate that. So if we go through each stage then. So this is the material that I chose to show you how to do Edge. It's from our Complete Mastery materials and Acquire lesson on abiotic and biotic factors. So this is the engage, and this is what students will see at the start of the lesson to get them interested. And basically they're asked then in the lesson, they're going to figure out why did megalodons, so giant sharks, go extinct, and they're helping this scientist to draw some conclusions from the information he's got. So at the end then they do the task, they're figuring out why did megs go extinct. So this is where the explain comes in. So students are going to need to use this skill of using evidence to solve this, to do this task. So we're giving them something that they will need this skill. We're giving them a reason to use it and where it fits into this lesson. So basically what they are going to do is they're going to come up with a conclusion of why megs went extinct. And there's lots of different claims that they could look at. So this is a student sheet that they get. So one possible claim could be that there was no food for the megs to eat. So that's one claim. And they'll need to come up with some evidence and some reasoning from this sheet to support that claim. And another claim could be it was a change in temperature. Again, what evidence and reasoning can they come up with from this sheet? And you can see that this is really quite a difficult task for students to do. So we're going to break it down for them and we're going to guide them so they can do this task independently. So the first thing you would do then is demonstrate, you would model the thinking process of how to do this using a worked example. So you are going to guide them through how to do this thinking process. And you really need to use an interesting context that's going to keep them motivated. But really importantly is to reduce that cognitive load. It has to be something that's very simple, something they already understand. So nothing to do with science. We don't want them thinking about the science. We just want them to think about the skill. So something simple and real life that they can relate to. And this is the example I chose. It could be anything at all, depending on your class, what their interests are. But I went with football. And so you could say that a claim is, Leicester City is the best football team in England, and my evidence comes from this league table. So let's have a look at the evidence then. So there's our claim. So you would go through them with the evidence. You are modelling this, but it's a really good idea to get students to give you some ideas about what they would say for each part of this. So what's measured in the table? So can they figure that out? Okay, it shows the number of matches each team's won. So what is the pattern it's showing? Get them to figure that out as well. And finally, does this provide evidence? So we're going through how would you use evidence then to support a claim? And the final bit that you're going to model is the reasoning. So does that evidence support that claim and explain why you think this? So you would go through the reasoning part as well. Now, all of those stages then we've put together in this scaffold called a thinking guide. So the next part of it, then you would show the students how you would actually use this thinking guide to go through those stages. And then they can use that then when you go back to the original task with the megs, they can use the thinking guide then to order their thoughts. Okay, so that's the next stage, that's the guide stage. So you're providing a support for students to do this task, to use this skill. And the final stage is the empower stage, which is where students are going to be independently practicing this skill. So later on, you're going to be using that same skill again in other lessons. And now they can use the guide to help them with the skill. And as they become more and more competent, you can remove parts of that guide or all of it completely. They won't need the guide anymore to do the skill. Okay.
Thanks very much, Gemma. I'm going to pause there and ask you, you've heard two strategies here related to two of the Rosenshine principles for minimizing, if you like, cognitive load whilst maximizing the processing for understanding. The first one was using analogies well. The second one was how to simplify skill teaching with this scaffolding process. It would be great if you could try one of them out and see if it works. So let's have a few ideas in the chat of things that you might do as a result of this webinar so that you apply what you've heard about and it doesn't get lost. So tell us what you think you might do, and then I'll tell you what's coming next. So we have next week, we're going to move on to session 3, which is the check for understanding. This is looking at questioning and also using the technology that many of you use, and how do we make sure what we've just said is being processed.